Hello everyone, welcome to torsionaltraining.com. I have the final module for this course. It's module 3, lesson 1. I'm going to teach you how to model a typical motor in diarrobes. So let's get started. So I have a pretty cool example for you guys today. I actually have a real shaft drawing of a motor. This is a pretty typical torsional data drawing that a manufacturer will give you. So now, if you recall, I'd mentioned in a previous module that manufacturers really never give you any shaft drawings, but they do give you enough information for you to carry out torsional analysis successfully. And so this is a typical example of a shaft drawing by a manufacturer. Very important information that you need for your torsional analysis is your geometry data right here, where you have your diameters and you have your lengths. The other really good information they give you is the torsional stiffness of the shaft. And the torsional stiffness is with respect to certain parts of the shaft. And they give you the material properties. So in this case, this is an AISI 4140 shaft, and the modulus of rigidity or the shear modulus is 11.8 e to the sixth, and then it gives you yield strength and ultimate strength for your stress parameters, and then it also gives you your total inertia uh, in pounds per feet squared, and the total length of the shaft, which in this case is 103.62 inches. Now, the other nice thing that they do is they give you sort of a nice schematic drawing, and where they show you all the specific lengths and the specific step changes in the diameter of the shaft, which is a really nice visual for you to look at when you're doing your modeling. So the drive end of the shaft starts from here, and then you have these step changes all the way up till here. Then you got this core of the motor, and then again towards the end, this is where the second bearing sits, and then the non-drive end of the shaft. So going by this particular shaft drawing, it's easy to put this model into diarrobes, but there are a few things that you have to do to get this model correctly, and that's what I'll show you in this particular lesson. Now, the first thing that you would do in any particular motor shaft drawing is you would start by breaking this particular shaft down into many components or many stations or many spans, right? So if you recall in diarrobes, we always have element numbers and we have station numbers. And so what you want to do is you want to break the shaft down into sufficient detail for you to do your modeling correctly. So what I like to do in my motor shaft modeling is I like to typically consider one or at most two elements for each span and for each step. So, for example, in this case, they have one span, right, which is the outer diameter is 6.25 inches, and the span length is 9.5 inches, and it also has a keyway of 1.5 inches. And then similarly, there is a second span, which is also 6.25 diameter and 1.5 length. So that's really starting from this point here to this point here where the next step begins, which in total is 11 inches. So why they break it down into 9.5 and 1.5 is because the 9.5 inches it has a keyway, and then the remaining inch and a half has no keyway. Now, in such a situation, you can break this down into two elements and have it as 9.5 for one element and then a inch and a half for the second element. For something like this, I typically just leave it as one whole element. And again, it depends on what you're trying to do. If you're trying to do a forced response analysis where you're going to be going in and calculating the stresses generated in this shaft due to the torsional excitation, then I would leave it the way they have it, in which case I would leave it as 9.5 inches and 1.5 inches. But for our purpose here, we're just trying to model this motor up. You can go ahead and leave this as one span of 11 inches. Then the next span is a 6.25 inches length and a 7-inch OD. And then the following span is a 6-inch length, which I believe is right here, and a 5.492 OD, and so on until you get to the end of the shaft. Now, you can see that what they have done here is they have they have a total of 9 spans, right? And what I have is a total of 11 spans. And so the difference between what I have and they have is in how they model the core area. So in my case, I really don't like to have very long lengths to be a single element. And this really goes is a throwback to finite element analysis where the preference is to add some more refinement in your model by adding more elements in a specific area when you are concerned about accuracy in that particular area. So in this case, what I like to do is I like to break down the core into more elements than typically what manufacturers will provide you in their model. And really, manufacturers, they don't care about how you model this up. You know, all they want to do is make sure that they're giving you all the information that you need, which is the diameters and the lengths to do your modeling. But it's up to you, the analyst, to decide what sort of fidelity you need in the model in order to get a good model with accurate results. So what I like to do is I like to break down the core area into a few elements so that I can capture detail a little better. In this case, you can see their span number 6 is 7.5 inches OD, which is this guy right here, and it starts and it's 52.3 inches long, and it starts from here. So from this point here all the way to here, to this point here, that is 52.3 inches of the core area. So what I like to do is I take that 52.3 inches core area and I just divide it by 4, because really you got 1, 2, 3, and 4 lengths that you can easily model well. So I take those 52.3 inches and I just divide it by 4, and so that's my span number 5, 6, 7, and 8. 5, 6, 7, and 8 over here, and then number 9, 10, and 11 are again back to what they have. Gives you a little more accuracy in your model, and I prefer it that way, and you'll see why this becomes important as we step through this lesson. Now, the other thing is, depending on where you are in the world, if you're using a motor manufacturer from Europe, then you're going to have your units in metric. In the US, typically the units are in the US customary, and up till now we've been using pound inches seconds squared for the inertia terms, and what they have provided us here is 2097 pound feet squared. So what I like to do is I like to convert everything into pound inches instead of leaving it in feet squared, because the Dyrov's model will be in inches, and so leaving it in feet, obviously you're going to have an error in your analysis. So convert your pound feet squared into pound inches second squared, and what you do is you go from pound feet squared to pound inches squared by multiplying by 144 inches squared plus feet squared, right? So you'll get this big value here, and then when you want to go from pound inches squared to pound inch second squared, you divide it by 386.1, which is basically dividing it by gravity, and so then you get 782.09 pound inch second squared. So the total inertia of this rotor, or this motor rotor shaft, is 2097 pound feet squared, or 782.09 pound inch second squared. So let's get started. Let's fire up Dyrovs and let's model this guy in, and then I'll take you through some important steps with respect to modeling these motors. So I fired up Dyrovs, and today we're going to do something a little different from the inertia stiffness models that we've been using in the past. And I sort of went through this sort of methodology of modeling in the first module, and I believe in the first lesson in the module, where we were just doing some simple inertia and stiffness calculations. And so we're just going to take that technique a little further with this particular motor. So the great news is we're out of the inertia stiffness models for some time, and we're going to actually model in the geometry that we've been given by the motor manufacturers. So I've copied over this motor shaft information that we have from the model here, and I've just pasted it into Excel here. And for now, we're going to focus on this table here on the left-hand side. Ignore this table on the right for a moment. We'll get back to this table. But this table is exactly the table that's presented to us in the shaft torsional data sheet. So go ahead and let's start getting this modeled in. So I'll minimize this, put it to the side, and I'll get die ropes to the side here. And the first thing we do, of course, always is click on data editor and pick our units. And since we're dealing with consistent English, which is what I like to work in usually, go ahead and click on that and click on motor model, right? And then click on material. And now this time we're not gonna call this a dummy material. We're actually gonna leave these properties in because we're gonna let Diarobes go ahead and calculate the inertias and the stiffnesses from the geometry that we put in the model. Now, one thing that needs to change in this particular model is the shear modulus because we have the number provided to us by the motor manufacturer. So going back to the PDF here, we have the modulus of rigidity, which is 11.8 e to the sixth. So this is the number that you want to use in place of the shear modulus here. So 11.8 e to the sixth. And you can change this comment to say motor material, right? So now we have the motor's material input in our model. So go ahead and click save and give this a name. I'll just call it motor dash one and hit save. And then we'll begin by putting in our shaft elements. So now, there's different terminology. People call elements the same as spans. So you can call this a span, you can call this an element number. It's the same thing. So let's get started here, and we have our information that we need to model here on the right. So type element, type 1, sub 1, material 1, level 0. Now we know the length here is 11 inches for the first element, so 11 inches. Our mass ID is 0 because there is no internal diameter. This is a solid shaft. Our mass OD is 6.25 inches right here. Our stiffness OD ID is 0 again, and our stiffness OD is also 6.25 inches because it's a solid shaft. And, for the lack of a better description, just call it 1. And then element number 2, sub 1, material 1, 0. The length is 6.25 inches. ID 0, OD 7, 0, 7, 2. And so, after inputting all this information on the right, your final mass elastic table should look like this. So this is 11 elements, and I have all the length information and all the mass OD information and all the stiffness OD information that matches the mass OD. And so we've modeled in the motor that was given to us by the manufacturer. So click on save, close, hit yes, and there's your motor. So, like always, anytime you start with modeling anything, you would like to validate the model that you have and make sure that it matches the information that's provided by the manufacturer. So go ahead and click on model, click on model summary, click on torsional vibration, and it pulls up the summary notepad file. And under this, scroll down and make sure that you have a couple of things correct. One is the length that you model in, is that correct? So the total length of the rotor is 103.62 inches, which should match what we have in the data sheet. And there you go, the total length is 103.62 inches, right? And the polar inertia should match what you have in the data sheet. So the polar inertia that's calculated is 18.7690. So this compared to what we have calculated is 782.09. So there's a huge discrepancy between what Dyrobes is calculating in the model and what's provided to us by the motor shaft data information. So what's different? What's wrong? Why are we so off from what's been provided to us by the manufacturer and what Dyrobes is calculating right here? So going back to the Dyrobes model, notice that we've put in only information of the bare shaft and we haven't put in any information of the actual core right here. And so the cores in motors are typically very heavy as far as weights and as far as inertias go. They add a lot of inertia to the models, and so they have to be modeled in separately. When we put in this geometry information data, we're not putting in any information of the core. Now, one thing that I do not like about this particular drawing is the manufacturer has not told you what the motor, or sorry, what the core's inertia is. So sometimes you have to really engage the manufacturer and you have to ask them to give you this information separately so that you can model them in separately. But what they like to do, most of them, is they just like to give you this 2097 number, which is the total inertia of this entire rotor, and then they let you try to figure it out on your own. So there are some methods that have been developed by people like Nestorides and Bicera, and there are some other great books out there that show you how to calculate the inertias of these rotor cores. And it's a pretty extensive topic. There's a lot of variation that are calculated in the inertias, and so it's part of the things that bring in a lot of uncertainty in torsional analysis modeling. And going back to some of my previous lessons, I talked about trying to take as many measurements as you can if you can come close to the machine. And this is one of those things that you want to try and get some measurements if you can, or you want to try and get after the manufacturer to give you more information about the core. The other thing that is interesting about this particular shaft drawing here is that they haven't given you specific fan information. Like a lot of these motors have some fans that are mounted on that have some inertia. So they haven't given you that information. They haven't told you where the fans are on this particular shaft, but they always make sure that it's there in the final number. Now, at the end of the day, my personal opinion is if you can measure and if you can get more information from the motor manufacturer, then you should go for it. It's not a good idea to always rely on these numbers because a lot of people in the field, including myself, have seen that these numbers are kind of close and they do come up to what they actually are in the field, but you'll still find a variation of say 10%, 15%, depending on what particular model you're working with at that time. But nonetheless, we will assume that this is correct and this is 2097 is the inertia. And so what's missing from our Dyrov's model is the core inertia. So what I like to do is I like to take this number, which is 782.09, and subtract the number that is calculated by Dyrov's, which is right here, from the large number. And so going back to my Excel spreadsheet, I have a tab here called Inertia Calcs. Click on that, and so the calculated shaft inertia is 18.769, and the total inertia provided by the manufacturer is 782.09. So I just subtract the two, and so the inertia that remains on this model is 763, and so I assign this the core inertia. And I have done this for a lot of models, and it works pretty well. And again, it's always best to try and get more information and also go in and calculate these core inertia yourself, but this is a little beyond the scope of this course. But you can safely do this and have a good estimate. Now, the other thing I like to do is I like to take this number right here and I like to divide it by 2 or 3 stations. So going back to the Dye-Robes model, the core sits in this general area here. So the core sits on stations 6, 7, and 8. So what I do is I take this 763 and I divide it by 3 and I have 254 pound-inch second squared. So let's go to the model and let's add in these inertias. So click on data editor and click on disks, and now we're putting in our inertias, which are rigid. We got station number 6, and we have a polar inertia of, I believe, 254.44, and you can call this core by 3 because it's core inertia by 3. Then again, rigid 7, same thing, 254.44, and then again another core by 3, and rigid 8, 254.44, and core by 3. So there you go. Hit save, close, right? And now you have your motor modeled in, and you have your core inertias also added here, which has been split by 3. Now go ahead and run this summary again to see what it calculates for you. So click on torsional vibration and now scroll down and you will find that the 3 inertias have been added in the model, and now your total 782.089 matches what you have in the shaft drawing right here. So now another very important thing to make sure that you've modeled this correctly is you should try and match the torsional stiffness value that's provided by the motor manufacturer, since you've already matched the inertia value. So they have a couple of notes here on how they do this, and different manufacturers do this differently. Some manufacturers will give you the torsional stiffness information from the drive end part all the way to the end of the shaft, and some of them will give you information from the end of the shaft to say about the middle part of the core. So if you notice, what they've done here is they've said torsional stiffness is calculated from the center of the core to the end of the shaft. So basically, they're calculating from around this area to this area. They're giving you the torsional stiffness information. So if I zoom out here a little bit, notice that the number that we have for torsional stiffness is 4.79 e to the 7th, and that torsional stiffness number is calculated from this span all the way to the end here. So this total span, so if you were to calculate the torsional inertia of each of these spans and find the equivalent torsional inertia, it'll calculate out to 4.79 e to the 7. So let's do that. So Diarobes is great about this. It can help you calculate the equivalent torsional stiffness information from one particular station in the model to another station in the model. So let me show you how you do that. So fire up Diarobes again, and under the Tools section, there is a tab here that says equivalent torsional stiffness from station I to station J. So go ahead and click on that, and it opens up this window here, and we want to now calculate the torsional stiffness from station number 7 to station 12, right? Because if you go back to what the data sheet says, it says that the torsional stiffness is calculated from the center of the core to the end of the shaft. So from the center of the core to the end of the shaft. So this length right here. So minimizing this, we want it from the center to the end. So number 7, so station number 7 to station number 12, and hit run. And so the number that we get is 5.3965 e to the 7. So now comparing this with what we have in the data sheet, they predicted a stiffness from this point to be 4.79 e to the 7. And we are predicting 5.39 e to the 7. So we're predicting a bigger number. And so this should make you pause and think about why you have a approximately 12% discrepancy, I think, between what the manufacturer is giving you and what Diarobes is calculating. So really what you have is a stiffer model. And when you have a stiffer model, you're going to have a higher torsional natural frequency. And this might be true, this may not be true, you never know unless you take real field data. But you want to do your best to be as close to what the manufacturer has provided you, because then at least as far as liability goes, you have something to go back to and say that, okay, the manufacturer provided me a particular model, and the data sheet says 4.79, and so it's very tough for you to defend a higher number in case something goes wrong or you have a torsional failure. So you want to do your best to address the differences between these two numbers. So I'll show you how I addressed it with this particular model. So let me copy this number here and compare it with what we have provided by the manufacturer. So I'll paste this here. And so we have about 12.66% difference between the manufacturer's value and what we have. So now this second table here is where I managed to close the gap between the calculated value by Diarobes and what the manufacturer has. And I closed the gap and I had a 0.62% difference. And I'll show you how I did that. So now going back to the data sheet, you have to read these very carefully to understand what they're saying. So the first thing that they say here is the torsional stiffness is calculated from the center of the core to the end of the shaft. So that's going to be from approximately this distance to that distance. And so they say the end of shaft to center of core, this right here, is 55.75 inches. So if I go back and I measure the length from the center or from my station number 7 here all the way to the end, which I paste here, is actually 47.62 inches right here. So I have 47.62 inches compared to 55.75 inches. So this torsional number here, the stiffness number here, is actually considering a length of 55.75 inches, while what Dyrobes is calculating for me when it does this calculation from station number 7 through 12 is actually calculating only 47.62 inches. So there's about 7 or 8 inches there that is not being accounted for in this calculation. And so that's where the discrepancy lies. So what I did in order to close this gap is since this tool gives you a nifty way of calculating a stiffness or equivalent stiffness between a station to a station, what I did is I adjusted the length of this element here so that I could go from this particular station number all the way to station number 12. So basically 55.75 inches to see if I can calculate the number that they have in the manufacturer. So let me show you how I did that. So I'll close this and I'll pull up my Excel sheet and go back to this mass elastic table tab here, and notice what I have now is what I call the Dyrobes model, the second table here, and it's almost exactly the same as this table with one key difference. If you scroll down to station number 6, what I did is I took off a few inches from this station and I put them in this element, station number 5. So if you compare the lengths, you have 13.075 versus 18.02, and then the 13.075 is then reduced to 8.13 inches. And so if I were to now measure the length from the end of the shaft, which is number 11, to the middle of the shaft or the center of the core, if I measure this, right, I have a sum of 55.75. So let me just calculate that here. So sum of this to here is 55.75 inches. So you need to adjust the Dyrobes model a little bit so that when you're calculating your equivalent stiffness information, just to compare against the shaft, you can shift the element just a little bit and still maintain the same length of the rotor, and then calculate the equivalent stiffness from that point to this point. So let me show you how I did that. Go ahead and click on Model, click on Data Editor, and click on Shaft Elements, and just change them to reflect the new table that we have here. So your final mass elastic table should now look like this table. So all I did is make a couple of changes here. I went for element number 5, which is here. I changed that to 18.02 inches, and then element number 6 is 8.13 inches. So all I did is I just shifted some of the length into this element from this element, but the total length of the shaft still remains the same. There's no difference. All I'm trying to do is just shift some of the length from this element into that element so that I can calculate the equivalent torsional stiffness information. So whenever I make a change like this, what I like to do is I like to do a save as and call it a different file name. So go ahead and call this motor-2, right? So that we have our original model still saved, and this is just a new model or a new iteration. And click Save, hit Close, hit Yes, and there you go. So now you have a slight difference. You can see now that this guy shifted a little bit this way, and so now you got more length from here to here. So now let's go ahead and calculate our equivalent torsional stiffness from station number 6, because remember, we're trying to capture a length of 55.75 inches. And so station 6 all the way to station 12 now has 55.75 inches. So from this point on till the end of the shaft is 55.75 inches, which is exactly what they say right here. End of the shaft to the center of the core is 55.75 inches. So click on Post on Tools, Equivalent Torsional Stiffness, Station I to J, and now we're going to go from number 6 to number 12, so 6 through 12, and hit Run. And so now what you have is a number which is 4.81962 e to the 7. So let me copy this and compare it to the manufacturer's number. So here, and paste it right here. And so now I have a 0.62% difference between what the manufacturer provided and what we calculated from Dyrobes. And so 0.62%, I can live with that kind of an error. That's really not a big error. 12.66% was something of a concern. It made me think that, okay, what's going on here? Why do we have such a big discrepancy? 0.62%, now you know what went wrong. So you have to learn to read these shaft drawings properly and understand what they're trying to tell you. Just by looking at this particular model, you would assume that this is the halfway point between the two, but in reality, it is not the halfway point, and the halfway point is with respect to the halfway point of the course. So you have to read these in that detail, and you have to be able to come as close to what the manufacturer predicts for his particular drawings. And the reason why, again, why you do this is because you want to protect yourself as an analyst. Tomorrow, if you have a failure of any kind, you should be able to defend your model and say that, okay, the manufacturer gave me 4.79. I I modeled it up and I compared mine with what the manufacturer had, and I had 0.62% difference between what they had and what I have. So this leaves us with two models now. We have Motor Dash 1 and Motor Dash 2. So the question is, which one should you use for your final analysis? It doesn't matter, you can use both. I only created this second model just to make sure that I had modeled this motor's parameters incorrectly. And I would probably go with motor 1 for the rest of my model. So for example, if this motor is driving some other unit through a coupling, then I would probably use motor 1, because now I know that this is the correct model. But you can use motor 2 as well. It shouldn't matter. Not a big deal. So there you go. This is our first lesson from module number 3. It's a very simple example, but really this is it. This is what it takes to model a motor. You just have to pay attention to a couple of key things about confirming your inertia information and confirming your torsional stiffness information and putting in that information in a Dyrobes model. And that should be it. The next lesson will be how to model a coupling, and then the final lesson will be how to put all three of them together. Now, you notice that I haven't run any torsional natural frequency or any interference diagram calculation, and truly you'll not be able to do that with your demo version. But really, the torsional natural frequency or interference diagram of a motor alone does not mean anything. When it's driving a machine, you really are concerned about the natural frequencies and mode shapes and interference diagrams of the whole machine. Once again, thanks for joining me for this course. I'll see you in the next lesson. Talk to you soon. Bye bye.